Hi everyone. So today we're gonna jump on to module 10, which is the module, well, your third digital module. So we had 8 where you got introduced to logic gate, 9 where you did some computation with adding and multiplying, and now we're gonna do a little bit more things that may be a little bit more abstract if you're not thinking about how computing works. But one of the application, well, one of the things you need is to talk to multiple devices back and forth, or have multiple devices able to connect to you. And this is called multiplexers and demultiplexers. So it's different from multiplying. So don't mix those up. Um, so when you're thinking about multiplexer, I always think about a telephone switchboard. This is very, very dated and historical, let's say, right? Um, where you have you have one telephone that used to be connected with a wire, and then you have another telephone on the other side. Normally, oh, well, you just connect those two wires together, the two devices can talk to each other, right? But you don't want to just talk to one person or one telephone, all the time. But sometimes you want to call someone else, right? So that's what a telephone switchboard does. It basically switches that wire from, let's say your output, your input and output on your phone to a different person's input and output on their phone. And that's essentially what a telephone switchboard does. You can see, I mean, it's just this picture is really dated. As you can see, but uh, but it's nice to actually have this kind of visual hope, right? Literally what they're doing is connecting wires from one to another, based on who's calling who. And then you can see that there are probably like 1,000 of these in this telephone switchboard. And there's used to be one of these in like every city, where someone has to physically connect you to a a uh, a device. If you want to call, you know, Joe, Bob, or whatever that name is. And then, and I think even before you didn't even need telephone numbers. You just literally tell the operator, I need to talk to Joe Bob. That's why there's a thing called an operator. Okay. And the operator would take your wire and run over to, where J is, or actually probably by last name B is, and figure out where Joe's connection is, and then plug that back in for you. And this is really kind of a very good example of how things get connected together electronically now. Even though you don't have a physical operator that does this, you have devices that can do this, as opposed to taking, maybe 10, 20 seconds to find that, you know, Joe Bob connection, right? These devices can do this in nanoseconds instead. So in modern day communication, and a good example of multiplexing is cell towers. So on a cell tower, right, the cell tower serves something on the order of maybe like 50,000 people, or if you're in a more crowded place, maybe 100,000 people. But the number of connections that a cell tower can make at each time is probably between 1 to 5,000. And the reason is that, right, the more connections that the tower can put in, well, there's also physical limitation and technological limitation, but there's also money limitation. Yeah, if you want to install a cell tower that can take 1,000 connection, it'll cost, a few $1 million or whatever it is. But if you want to build one that can take 5,000, then it costs 5 times as much, because you have 5 times as many wiring in there. Okay. And the thing is, right, most people are not talking on their phone all the time. At least I hope not. Uh, and what the cell phone company does is that they multiplex these connections, so that when you actually dial to a cell phone tower and say, I want a connection, right, it'll dedicate that line, one out of the 1,000 line for you. And then as soon as you're done, it connects to someone else. Okay. And this is how cellular network actually is able to serve more customers using the same infrastructure. So an example of this, it's interesting that the book gives examples of chips that are pre-made and then tell you how the chip actually works. But so an example of this that would be on someone's breadboard if they're building something that needs a multiplexer is the 74151 chip, which is a 8-to-1 multiplexer. So there are 8 possible inputs here. Okay, and you have 1 output here. This Q bar is just going to be the opposite of the output. That's the notation denotes, right? The bar is the opposite. So if Q is 1, then the Q bar will be 0. If Q is 0, then Q bar will be 1. Okay, and down here, well, there's an enable sign. Let's not lump that into there. Okay, so let's talk about these are the 8 possible inputs. So this is, just think about this as 8 different cell phone that can be calling the cell phone tower. These are the cell phones, right? Okay, and this is the connection, this one connection for the cell tower, right? Let's say we have a pretty cheap cell tower, right? And basically what you want to be able to do is to, I0, input 0 is coming, wants to call someone, it makes that connection to Q0. Oh, I0 is done, so you disconnect it. And now I4 wants to talk, and then so I4 will be connected. You may see some of this. When a cell tower is very busy, it will still try to make the connection, and what it does is that it gives the connection to I0 and then give it to I4, and it just oscillate between the two. And you may have heard this effect where you're kind of talking like a willowy, like you would lose like half a syllable at each word. You may have experienced that yourself. But anyway, that's just a little interesting effect of these multiplexing technology. But the other important thing is that, well, how does it know which connection to make? And the way that is determined is using these A's. So A's determines which connection gets made. You notice there's 3 A's. 3 A's gives you 3 bits, and 3 bits can go from 0 to 7, which gives you 8 different connections to choose from. So basically, if all these are 0, right, the binary number for that is 0, then it connects to 0. But then if you flip A1 to 1, it connects to 1. If you flip A0 to 1 first, and then A0 to 1, now this number is 3, then makes the connection at 3. So this basically chooses which channel gets enabled, while it gets connected. I don't want to save that enable word for something else. Down here, you also have this E bar thing. This is the enable, opposite of enable. So when there's a bar here, this is actually a good teaching tech sheet moment. So when there's an E bar, right, that means it literally means enable but opposite, right? Okay, so that means not enable. Okay, so when this is true, the thing is off. When this is false, right, true, right, then chip is off. When this is false, the chip is on. And why do we use enable bar as opposed to just regular enable? Right? Because now if you wanted this chip to be enabled permanently, you just have to tie this to ground. Because ground means 0. 0 means false. When it's false, that means the chip is on. So it's a way to passively, right, be able to enable the chip without drawing a little bit of current all the time, by making it enable as opposed to enable bar. Hopefully that logic makes sense. It's just a little simpler to connect to things to ground and a little bit more power efficient. Going back to more applications. So multiplexing is really how you actually create random access memory. So on a memory module like this, okay, this little memory module, I think it looks like a laptop memory. Okay, you have all these different memory chips on it that has billions and billions of memory channels that you want to read out, but you have limited numbers of pins that you can send the data to, right? And this is how you deal with multiplexing. So this PMIC, well, actually, it's probably just a 5120 chip. This is a multiplexer chip. Okay. Okay. The short for that is MUX. People call it MUX, DMUX, MUX and DMUX. Okay. And that's basically how I think these are 188 pin SODIMMs can be able to have access to billions of different memory channels because you're basically only connecting to some of them at a time. Okay. So that's another more internal usage of multiplexing. Okay, so let's see how we can make a multiplexer out of our logic gates. Okay, we'll start off simple. Let's do a 2x1 multiplexer. Okay, and this little circuit, hopefully we can figure out how it works because, right, so I'm gonna write the capital version of here. Okay, and then I think previously they used A, so I'm going to use A0 here. So for a 2x1, meaning you're only choosing between two different inputs. Okay, all you need is 1 bit for your selector thing, your A's, right? That allows you to choose, oh, I want channel 0 or channel 1. You don't need to go to 2, right? Okay, so that's why there's only 1 here. Okay, so let's do the little truth table of this. Okay, that's a really good way to learn how a circuit works is by drawing the truth table. Let's do that in black. Okay, and this truth table, we have 3 different possible input. Oops. Okay. In fact, what I'm going to do, okay, I'm going to do a few of these and then we'll see the pattern here. Okay, put A0 here first, high 0, high 1, and then we'll figure out, let's make this X, well, Y is already used, of course. Let's make that Q, okay? X, and then Q, and then finally we have Y at the end, okay? All right, so what happened is that if this is all 0, what happens is that, well, you have 0 coming into this, okay? And what I'm going to do is I'm going to draw a little circle here with dotted line. It's not a real knot, just so that I know what this opposite thing is going into, okay? So on this first gate, right, you have 0, 0, and AND of 0, 0s give you 0, okay? And then on the second gate, you have 0, but then this, oops, sorry. Oops, I1, not I0. I already made a mistake. So remember, this was inverted. So if A0 is 0, this is actually 1, but it's an AND gate, it still gives you 0, okay? The Q is also 0 because now your input is just 0, and then you have a regular input to A0, which gives you 0, okay? And then an OR of 0, 0, of course, is 0. Okay, so let's do a couple of more of these, just so we can select things, okay? I'm going to keep A0 equal to 0, okay? But I'm going to make I0 equals to 1, okay? And the rest the same, okay? Now A0, right? To figure out what X is the AND between I0, which is 1, right? And then whatever the opposite of A0 is, which is also 1, right? That's the opposite. So you get 1 here. And then the Q stays the same. And then now the actual Y output is 1. Okay? Right? So you notice that, right? When this key for the selector channel, the A's, right, is on 0, basically whatever the output is follows whatever input 0 is. Okay, so let's do one more example. Okay, you can fill this out because there's going to be, so there's 3 different inputs. You're going to have 8 different rows of this. I'm not going to go through all 8 rows, but I'm going to make the, maybe the A0, not A0 equals to 1. Okay, but I'll keep the rest the same, right? I'm not going to change anything. And let's see what the output is at the end. Okay, now A0 is 1, right? So that means the opposite of A0, which is the input for X, right, is now 0. So X turns to 0. But then Q, right, Q is from the input of I1 and A0, right? This is also 0, 0. It's 0, 1, okay? The 1 is from A0. So that your Q, since it's an AND, is still 0. So flip back to 0. So now, right, with A0 equals to 1, right, your output is following I1 now. So let's do one more, right? 1, 0. Well, let's keep 1. Let's keep I0, 1. And then let's see what happens when I1 goes to 1. Now, let's change just so that's different, okay? I'm going to make I0, 0. Okay. All right, now, right, X, right? X is still 0 because you have 0, 0 as the input, okay? And now, right, Q is I1 and A0, which are both 1s. Now you get a 1 here, and then you get an OR gate over here, okay? So now you can see that, right, when A0 is 0, the output follows whatever I0 is. If A0 is 1, if the output follows whatever I1 is. And this keeps going. So if you have, you know, A0, A1, right? In fact, I think there are more examples of this, okay? If you want to have a 4x1 multiplexer, okay, right? Now it keeps changing the letters. The selector bits, right? You need 2 bits instead because you need to go from 0, 1, 2, and 3, okay? And those 0, 1, 2, and 3 basically select which inputs you use in your output here, okay? And notice that these are actually also 3 input gates, right? And the fourth one is actually a 4 input gate, okay? That's necessary in order for you to have a multiplexer. And remember, it's pretty simple to make, you know, if you can design a IC that does a 3 input or 4 inputs, but you can also put, you know, two input gates together, two input AND gates together to make 1 3 AND output gates, right? And then if you need 4 input OR gates, you need 3. You actually need 3 regular OR gates, and you can basically kind of double them up to make the 2 or 3 input gates. Okay, so these are pretty easy to make. It's more efficient if you don't make them out of separate gates, but you know, if you in our lab, we're not going to buy a bunch of 4 input gates just to use it once, right? Okay, so and then this goes on, right? You have a 8x1, 16x1. And this is the reason why, okay, so often back when I was working in the computer memory industry, always ask like the more technical, more knowledgeable people, say, you know, I can buy a 8 GB RAM and then 16, but how come I can't buy a 12? And that's because these multiplexer, right, every time you up the multiplexing, you double from the base amount, right? So you go from 2, 4, 8, 16. It's not because, oh, I only have space for, 16 chips and no space for 12. That doesn't make sense, right? Because you can fit less on the board if you need to. But, right, this multiplexer chip really determines that it's always doubling of the base amount of the previous memory size because, right, these multiplexer always doubles in the number of channels they can handle. And why waste extra channels if you don't have to, right? It's just an efficiency issue. Okay, so this is how you would do it on a breadboard, right? A bunch of AND gates and an OR gate and a bunch of NOT gates, okay? I'm not going to force you to build a 16x multiplexer, not multiplier, multiplexer on your breadboard. What we will do, okay, is we will do it on FPGA, okay? So this is an implementation of a 4x1, I think. So just so that we can see how it works, okay? And hopefully you can literally see the link between the two, okay? So what I'm going to do is I'm going to define a bunch of wires. I probably should have defined them the same way. So x1, x2, x3, these are the input. These are like the I's. Sorry, I just changed the letters. As you can see that these letters, they're just variables, so they're meaningless, but hopefully you can find the continuation. These are the inputs, okay? And S are the selector select channel bits, okay? Okay. So what we do is, since we start off how this logic works, let me zoom out a little bit, right? So first thing you have to go in, right, is these ANDs of the inputs, okay? And you notice that this tilde, this tilde S1 means the opposite of whatever S1 is, right? Okay, so if S1 is 1, you do the opposite of that, okay? So this 3 input AND gate that I wrote down here in Verilog, right, is literally this AND gate here. And you have this, right? I'm going to change the letter once again. Sorry about that. Right. So S0 opposite going to the AND gate. That's what I have here. Right. Right. Opposite of S1. So that's what's going in here. Right. And then I have X0, right, going in there straight without the opposite. So this is the one. This is the first AND gate up here. Okay. And then you can see subsequently, right, I just, pipe in the right logic, whether I use S1, S0, or the opposite of S1, S2, S0, S1, right? And then I use the correct input for that in order to select different bits. Notice that, so it, not S0, not S1, not S0, that's equivalent to 0, 0. Not S1, S0, you see this? That's equivalent to 1. I should probably have written this in binary, actually. So this is in decimal, right? This is equivalent to 0, 1. This is equivalent to 0, 0. And then this one, right, is not S1, but regular S1 and not S0. That's equivalent to 1, 0. And these are going to equivalent to 1, 1, okay? 1 binary. Okay. And then and then you take all 4 of these OR gates and you pipe them all into a single, all these AND gates, and you pipe them all into a single OR gate and assign it the output, which I call Q instead of Y. Sorry about that. Okay. And I'm just going to, just to check it so that I can see how it works. I'm going to put Q as the LED, something like that. Okay. And you get to play around this in the lab. Okay. So hopefully this will work out pretty well. Okay. This is the way you would, you basically translate a circuit into Verilog code, and then Vivado actually take this, translate it back into a circuit using when you do the synthesis, okay, and it does the wiring for you when you do the implementation, right? Remember how that process worked? Okay. So I'm going to show you a little bit a cleaner way to do this is by using vectors instead. So vectorization, right, makes it a little bit cleaner. That's why we use it in even in intro physics, when we have, instead of XYZ, we say X bracket, and that, and the array can be, 0, 1, 2, or 3 representing the XYZ. Okay. Right. So in this case, right, we shorten this by making X basically a 4-element vector. And in Verilog, you have to define the MSB to the LSB with a colon between them. And you have to do that before the variable itself, okay, when you define them, okay. When you're actually using them, you put it after, okay. So this way it's actually very clear whether you're defining a variable or just using a variable, okay. These are rules that are very sensible. And I know annoying some people who are more used to, more um, user-friendly coding languages that's currently being used these days anyway. Okay. All right. And this is very similar where then you have the selector bits, which is 2 bits in this case. Well, so the MSB is 1, and then the least significant bit is 0. Okay. Representing the 2's place and the 1's place. Okay. And then now I'm going to introduce you to this new operator, the double equal. This is the equivalency operator. So notice that up here, right, I tried to highlight this last time, the equal sign does not mean an equation here. It's literally putting what's on the right-hand side into the left-hand side. It's a assignment operator. That's why they put assign even on a in Verilog, just so that it's clear that you're assigning a variable into another one. Okay. In this case, let's do that in yellow. Right. This is the equivalence operator. It compares the values on both sides and say, is this equivalent or not? If it's not, then you move on to the next thing. Okay. So what this first comparison is doing is that it's comparing the 2 bits in SEL. Is it equivalent to a 2-bit binary with 0, 0? So it's basically, if select is 0, 0, and then you're comparing it to 0, 0, then that's going to return a value of true. And then that will basically get you through this question mark, and then it'll assign x0 to be your q. Okay, let's do one more, right? So in the case where, let's say select is 0, 1 instead, meaning, right? Well, okay, I'm gonna write it out. Okay, the MSB, right, is equal to 0, but the LSB is equal to 1. Let's say in that case, right? So the vector of SEL, you can write it this way. So 0, 1, like this. Okay, right? If that's the case, it's when you check for this, it's not equivalent anymore because 0, 0 is not equivalent to 0, 1. Okay, therefore it goes to the next check, which is on the next line. Okay, and that's going to check, oh, well, is select equal to a 2-bit binary? 2 apostrophe means 2 bits. Okay, is it equivalent to 0, 1? And in that case, it's going to be yes. So now, right, the output is going to be connected to x1 instead. Okay, and this keeps going on like that. Notice that the last one, I don't have to check whether or not it's going to be 1, 1, because I already exhausted all the possibility. So, and this is actually a better way to code things, so that way that your output always have to be assigned something. Because if you have a check and you have made a mistake in your code, let's say you just copy and pasted this line without changing that 1 bit, right? Then there could be a case where it gets stuck. It's like, well, I don't know what to assign Q. It'll either give you a error when you synthesize, or your whatever thing you're programming the FPGA will just get stuck, which is not good, right? Right. So this is a way to use vectors to simplify your code. You can argue that it complicates the logic, but when you start dealing with like 16 bits, for example, right, you don't want 16 of these ampersands, right? That'll just confuse. That's more confusing than dealing with the vectors. So make sure to adopt to vectorization as basically like your second step. You learn the basic logic, like what we did up here, right? By just looking at this circuit and then mapping it to the code. Okay, and the very next step should be you vectorize it so that it generalizes to higher number of bits. Okay, let's talk about demultiplexer. I'm a little on time already. Demultiplexer does the opposite. Okay, so instead of taking a multiple inputs and making it one output, it takes one input and it could send it to multiple outputs. Okay, the example chip is going to be the 74138, which is a pretty old chip already, to be honest. Okay, and what it does is that it takes these E's actually serves, I think this E3 probably I think it serves as the input, and then the A serves as the selector bits, so 0, 1, 2, 3, 4, 5, 6, 7, 8, right, depending on the bits of here. And then you have 8 outputs on this side, okay? The way you implement a demultiplexer using AND gates is kind of the same. You have the opposite, where this is a 1 by 4. So when you say 4 by 1, it means a multiplexer. When you say 1 by 4, it means a demultiplexer. So you don't even need to specify that. Okay, so you can take one input here, right? And this one input is connected to every AND gate, but then the selectors, right, tells you which one to turn on and off, depending on how the selector is switch. Okay, and this is what you're going to do in the lab. You're basically going to implement this demultiplexer in Verilog code and then vectorize it. And then this will be a fun little exercise in the pre-lab and in the lab. Okay. All right. So one last thing to cover is the analog multiplexer, demultiplexer. So multiplexing, when you're picking the input as 0, 0, 0, 1, 1, 0, 1, 1, that's inherently a digital thing, right? But the data that you're sending it does not necessarily have to be digital, right? You don't have to just send ones and zero. And this is where you can have analog multiplexer. And when they say analog multiplexer, it's only the data signal that's analog, okay? The selection of which channel you're using is still discrete and therefore digital, okay? And so this DG412, which is a single pull, single throw multiplexer, okay? How it works is that, so these are MOSFET gates. If you're really interested in how MOSFET gates work, MOSFET transistor works, you should watch this video from the same Sabine Civil Engineering. I think that's the channel. And then if you just search for MOSFET, you can watch this video. I'm not going to play it because otherwise Google will not like that, because I'm playing someone else's video on my video. Anyway, so if you're really interested in how that works, but the thing I need you to know for this particular circuit is to just understand that, okay, if the gates is pointing out, okay, that means it's a positive edge. This transistor is a positive edge trigger transistor, meaning when your signal goes from low to high like this, it turns this on, okay? This turns on this side. When this little arrow goes into the transistor, right? It's a negative edge, meaning that it turns on when you when the input voltage goes from high to low instead. Okay, so let's do the case where it turns on and see what happens. Okay, so that means these are connected together. So when this voltage go from VSS to VDD to digital, right? Basically think of this as a solid wire, right? Since this is a negative edge trigger, this doesn't do anything, so it doesn't get connected. This is also a negative edge trigger, right? But so this doesn't get connected either. But you'd have the connection up here, from here all the way down to here, right? And now this is pointing out, so this is also a positive edge, so that gets connected. So what happened is that the data basically gets sent from D to S, okay? And that's how you can have a analog signal that goes through these things without dealing with digital gates, right? Remember when we did the digital gates version, these were AND gates, right? You cannot have analog signal flowing through it, but you can make the gate out of transistors, and then it'll physically, right, connect the data to whatever you want to send it to, your D to S in this case, okay, your receiver. Okay, and that's how you built up a a analog multiplexer, okay, by having multiple of these. Well, there's a little example in the textbook. Maybe we'll discuss that in the lecture, in the pre-lab, okay? I'm out of time, so I'm gonna stop this video, and I'll see you next video when we talk about digital memories.